Right, now we come to the penultimate lecture in the series. It's going to be a little different, not so much theory. We're going to deal with some of the methods that are used to prepare data for analysis and get on to the question of how you do the fitting of a mechanism to that data in real life to get the things that you actually want out of it. In the last lecture, we'll talk about fitting real data and some of the inferences you can make from it. Okay, now, of course, in analyzing real data, we're entirely dependent on computer programs. We started writing programs for analysis of single channel data around 1979, 80, and for 11 or so years, they were dependent on PDP-11s, which were the size of a small room and had removable disks which were huge, with a capacity of about 2 and a bit megabytes. Around 1990, we moved to PCs, and we wrote a whole suite of programs for analysis of single channel records. In fact, my major role in the Cahoon and Hawkes work was to translate them into usable programs. Of course, up till 2000 or so, these were all DOS programs, and some of them still are. You can run them still, but they're not ideal in modern terms. We had analysis programs scanned for idealizing the raw record by time course fitting, EKDist, which fits distributions empirically with no reference to mechanisms. We had theory programs to calculate the consequence of specified mechanisms, macroscopic responses, burst durations after channel openings after a jump, calculating the correlations between open times, shut times, and so on, and for simulating the output from scan. Best of all, by late 90s, we developed HJCfit, and this does what we actually want. It fits the rate constants in a specified mechanism to the idealized records. And that is the basis of most of what's been done since. We also had a thing which would collect graphs from any analysis and plot them out automatically. This was the relationship between our programs. You can see it on our 1mol site. It doesn't really matter now. What we're going to do is essentially to talk about a very brief account of what's in the Cahoon and Sigworth paper, which was part of the single channel recording book, 1995. It was, that in fact is my most cited work by far, about 1,500 citations according to Google Scholar. But it doesn't count in the eyes of metrics people because it was in a book. We have a website which is devoted to our single channel work. It's not on the UCL site because UCL made it wretchedly difficult to keep anything up to date. So we just set up a site of our own, owned by Lucia Civilotti, called onemol.org.uk. And you can find a home page, about page, programs. You can find a description of the programs there, and you can find links to download all of the source code. We always had our source code public. In the old days, you had to send it on floppy disks. Now you can just be downloaded, of course. You can also find links to most of our publications. The publications tab has the experimental one, the single molecule theory papers. This is the drop-down menu shown drop-down. Has the Cahoon and Hawkes theory papers. And there's another page for some papers about p-values, which have nothing to do with single channels, just my latest hobby to keep me off the streets once I'd retired from the lab. There's also a page which was devoted to the summer workshop, which we ran, and which these are the lectures from. So if you can go to onemole.org.uk, you can find out a lot more. Okay, so the first job you've got when faced with a single channel recording is to idealize it. That means to make a list of the open times, the shut times, and the amplitudes of the openings. And there's several ways of doing this. One is threshold crossing. The second method that we use is time course fitting. In threshold crossing, a transition is deemed to have occurred when the trace crosses a threshold level, which is usually halfway between open and shut levels. So it's no good for anything that has subconductance levels, for example. And it works well only for events that are longer than about 1.5 filter rise times. It doesn't measure the amplitudes well, and it can be fast if it's automated, but automation is pretty dangerous, I think. With time course fitting, what we do is measure the step response function of the recording system, and it's used to fit the trace. I'll illustrate that in a minute. So we've got a long record like this, and we want the open and shut times. So with threshold crossing, you can illustrate it here. These are two short openings, two more short openings, and a longer opening. The first one, when filtered, looks like that, so you miss it altogether. In the second pair, the first opening is a bit longer, so it just goes over the threshold. It's detected, but it's measured very badly. Its duration is measured very badly. And so what you get out of this is that, which is badly reconstructed there, but quite well reconstructed here. Here are some actual records. In this top one, we see a long opening downwards this time, and then a short opening. And this is what it looks like when it's filtered below. Here we see a long opening, a short shutting, and then another long opening, and then a shutting. So the short shutting is very attenuated in amplitude, again, because of the filtering. In fact, if you have a short opening, a short shutting, and then a long opening, it can look something like that. And if you have two short shuttings in succession, it can look very like a sublevel opening. That these some of the hazards, there'll always be a few ambiguous things. This shows an example where some examples in which threshold crossing can work quite well. Here's a long opening, it's downwards, the dots are the signal, the digitized signal. That line is the shut level, this is the open level, the dashed line is halfway between them, and the points at which they cross are a good measure of the length of that opening. Here's two more distinct openings. These vertical lines mark the crossing points where the threshold is crossed. It works quite well here too. There's one point that should be made, if we blow up the shutting reaction with a much expanded scale, you can see that there's a digitized point here and a digitized point there, but nothing actually at the threshold. Now, what you should clearly do is do a little quick linear interpolation to find the time point at which it crosses the threshold. Some programs don't bother to do this. They just count the number of points beyond the threshold, and that produces values which are all rounded to the duration, which is equal to the interval between the samples. And that just throws away information. It's silly. Also, some of the other methods which have been used, in particularly by Auerbach's group, segmented k-means method for detecting open and shut times, they also do that, and it just throws away a lot of useful information. Here's some examples in which threshold crossing doesn't work at all well. Here there's two clear brief shuttings which are not detected at all. And this is the worst example of the lot. In this case, there was a subconductance level which happened to be about halfway between the shut and the open level. And since the 50% threshold goes right through that, you get a whole bunch of completely spurious transitions discovered. These pictures are very old now. They're all taken from a storage oscilloscope with a Polaroid camera, believe it or not. But they illustrate very well the problems. So for time course fitting, what do? We want these are theoretical things as a step input to the patch clamp recording apparatus, and here's the response after it's been filtered. This is a shutting which produces exactly the same sort of thing. If we add those two up, we get a pulse. The shutting occurs after the opening. We get a pulse, and that produces an attenuated output like that. If the pulse is longer, the shift here for the opening and the shutting is greater, then you get a nice flat top, but with a transition period. You can measure this by inducing a square wave input by holding a triangular wave generator close to the head stage. It has to be a very good triangular wave generator or you get artifacts. And you can actually measure empirically this response of the whole apparatus to a step input. That's the ideal way to do it. In fact, very often the limiting factor in the shape of this response is the filter you use, usually an 8-pole Bessel filter. And in that case, you can just use for this the theoretical response of a step to an 8-pole Bessel filter, which is a well-known expression. And doing that, you can fit the whole of this record in one fell swoop in this example. The points here are the data. The solid line is the fit to it. You see we fitted a short opening there, a short opening here, a longer opening here, transition to a sub-level, shut again, an opening to the sub-level, and so on. And having defined which bit of record you want to fit, this can all be done automatically by least squares. It detects the transitions and fits the durations. It also fits the amplitude, so that amplitude gets entered as one amplitude in the result. This gets entered as another amplitude in the result. And it also fits the final baseline, so you can allow for baseline shifts quite nicely with this method. This is what it actually looks like on the screen. The yellow arrow here shows where the fit is got up to. The channel at the moment is shut. This opening here has already been fitted. You might have to turn the lights down a bit because these are single pixels representing the digitized signal. So they're not terribly bright, but they look good on the screen when in real life. So this is actually found by rolling the display along. This is actually written in floating point assembler, which is one of the great triumphs of programming in the 80s. And whenever it crosses this line, which you can set the height of, it thinks there might be a transition there, and the display will stop scrolling along, and you can then fit it. It works from the numeric keyboard much, much quicker than the mouse, incidentally. If you've got to do it repetitively, and you've got to fit several thousand of these, so you want it to be quick, you just say, hit the 4, fit automatically. And what you get then is this. The region which is fitted is shown by this red bracket up there. And the least squares fit of the transitions in this period are marked by the red line. So you fitted here and a bit of baseline there. You fitted an opening here and recording its amplitude, transition to a sublevel, a short shutting, back to the sublevel, back to the sublevel again. And then there's a transition to the full open level. And then there's a very short shutting here and a somewhat longer one there. The problem with the short shutting is that you don't know that it actually goes to the baseline. Similarly, with this short opening, you can't tell whether it's going to open to the subconductance level or to the full level, because it's just well short of either of them. So what do you do in that case? Well, the best thing you can do, this is what we did do anyway, is to suppose that these two openings are the same amplitude as the nearest fully resolved opening, which is this one. So we assume that these are going to the full open level. This, of course, only matters if there's subconductance levels there, so it matters for NMDA, not much for other sorts of receptor. And this green dashed line shows that that's the assumed amplitude to which this was going, and likewise for this one. And if you assume the amplitude, then you can measure its duration, even though it's well short of the 50% threshold, for example. Likewise, this short opening was assumed to be the sublevel because the nearest fully resolved thing is the sublevel. These marked with blue arrows are assumed to be complete shutting. It's a very short shutting. You can't tell whether it's going to go all the way down to the baseline. This one only reaches to there, for example, but it was assumed it was a complete shutting, and that's a pretty reasonable assumption on the whole. The calibrations here are 1 picoamp and 5 milliseconds. And there's a list here of what's going on. The latest transitions are 2.3 milliseconds to 0 picoamps. That's a shut period. 44 microseconds to a full amplitude, and 148 microseconds to assumed 5.27, which is a full amplitude. These little blue arrows mean that the amplitude is assumed. So you just go through your 50,000 things that way, and it takes a day or two, and it's quite tedious, but it's the best way to do it by far, I think. Before doing that analysis, what you should check is stability plots, because you're going to assume that the record was in a steady state for the analysis, and it's best to check that. Here's a record from an NMDA receptor. These are the individual amplitudes. Each point is a single measured amplitude. And you can see that there's a subconductance level here. They're quite scattered, in fact. And they look very steady. The amplitudes aren't changing with time. That's going from 0 to 4,000 openings. Oops. The other thing you want to check is the dwell time stability. These stability plots were introduced by Carl Magleby, I think, and it's an important check before you do the analysis. These are the individual open times, of course, are too variable to make them worth plotting. These are running averages of 50 open times, which is why they're sort of jagged. You can set what the running average should be taken over. And you can see that the open times here are really very steady. The shut times, on the other hand, seem to be decreasing a bit. And consequently, the probability of being open, which is calculated from these two, is actually increasing a bit. So it's not a perfect record. This is another record from an NMDA receptor, which is absolutely terrible. For some reason, you can see that there's a full level and a sub-level again, but for some reason they suddenly switch to a lower value at that point. And at the same point, the shut times go absolutely haywire. And so the P open does likewise. The open times, again, are quite stable, which is quite interesting. So that would certainly be rejected for analysis. For a nicotinic receptor from a frog end plate, you can get much better results. The amplitudes stay dead constant. The shut times and the open times stay constant, and so the P open stays constant. So that's ideal. We could do this in our EKDIS program, plot those. Okay, so now let's get on to some fitting. We generally in this area aim to fit by the method of maximum likelihood. And I've mentioned it before, but I'll describe it again briefly. Bayes' theorem says that the posterior probability of a hypothesis, the probability after you've done an experiment, is equal to the prior probability of the hypothesis. The probabilities it was true before the experiment was done times the likelihood. Now, this, of course, was controversial when it was first written in 1764 and has continued to be, because you can't talk about the probability of a hypothesis being true in the usual long-term frequency definition of probability. So, clearly the sun goes around the earth or the earth goes around the sun, and there's the probability of one of those being true rather than the other can't be interpreted in a frequency sense. It doesn't go around the sun 95% of the time. Luckily, Ronald Fisher, the great statistician and shocking racist, provided a way around this, and that's to choose the hypothesis with the greatest likelihood. And what that means is you choose the hypothesis that makes your observations more probable than any other hypothesis. That's the method of maximum likelihood. So the likelihood of a hypothesis is the probability of the data given that hypothesis is true. The likelihood isn't a probability, strictly speaking, but it is a measure of how plausible your hypothesis is. Of course, to calculate the likelihood, you have to know the distribution of your data. That's rather rare to do that, so people just assume it's Gaussian or rather cavalier sort of way. But in the case of single channel records, the data are distributions, so it's an ideal method to use. It can be used in two different ways, depending on what it is that you're going to estimate. If you just fit a distribution of open times with exponentials, then you can estimate the time constants and the areas for those exponentials. But the time constants are, well, they're eigenvalues of a submatrix of Q, as we've seen, and they can't be interpreted directly in terms of mechanism. What we want to fit is the reaction mechanism itself, so that rather than getting the time constants and areas of exponentials, you get the actual transition rates, the transition rate constants, which govern the movement of the mechanism between different states. In other words, you want to estimate the elements of the Q matrix. That's quite a different thing and much more valuable. Before going on to that, I'll just say a word or two about two other sorts of distributions you get from the raw data. Distributions of amplitudes. You can just plot the amplitude of every one of these points, taking the shut level as 0, and that gives you something that looks like this. In this case, there was a small number of double amplitude openings where two channels were open at once. So that's the amplitude for one channel, that's the baseline. There's a smear here because of the non-instantaneous transitions from shut to open. If you fitted it with our scan program, then you know how long the transitions take, because that comes from your step response function. And so you can exclude all the points from the time when it's going from shut to open. And that gives you a much cleaner histogram. You can also see that in this particular case, that the channel is noisier when it's open than when it's shut. This is an interesting phenomenon that's often been observed to various extents. There's another way of plotting amplitude distributions, which I think is much better, and that is to take not the distributions of the original points, but the distribution of the amplitudes that are fitted in scan. If there's more than one amplitude, this will give you different areas, though the amplitudes that you measure, the peaks ought to be much the same. And that's because if you're plotting the distribution of all the individual data points, then a long opening will contribute more data points than a short one. Whereas if you're measuring the amplitudes as in SCAN, then you get each opening contributes one amplitude. Here's an example of a channel of about 6 and a bit picoamps. That's plotted over the whole scale up to from 0 upwards. You can see that there's nice tight distribution of amplitudes. If we blow up the bit between 6 and 7 picoamps here, we can see that this Gaussian fitted to it doesn't in fact fit particularly well, though it's the distribution is pretty symmetrical, so this will estimate the average amplitude quite accurately. You can actually work out the theoretical distribution of these measured amplitudes. It's done in the Cahoon and Sigwarth chapter, but I don't know of anybody who's actually used that distribution to fit. It's not generally necessary. It's rather complicated. This occurred in one of the earliest lectures, a distribution of open times fitted with a simple exponential probability density function. Doesn't fit very well, especially at the low end, but that's what we can do. I should emphasize here again, we've seen this slide before, but I'll emphasize it again here, that you very rarely see exponential distributions in any publication, at least any publication after about the early 1980s. This is an exponential probability density function. That's its equation. We've seen that many times. But it's not a very convenient way to plot it. So the distribution of the logs of the durations is what's usually plotted. So we have a log scale here, 0.1, 0.01, 0.1, 1, and 10. And if you plot the same curve in that way, it looks like this. There's a peak actually at the time constant, which was 1 in this case. So this is what you see in experimental papers these days. But if you see that, remember that the actual shape is that exponential shape. Well, usually the square root of the probability density function is plotted because this makes the precision similar in different bins, but the shape is qualitatively very similar. This shows from our earliest work in 1981 or so, a distribution of shut times, and this really illustrates the beauty of the log plot. This was the distribution of all shut times up to 1500 milliseconds, 1.5 seconds. It looks as if it fits okay, except there's a huge excess in that first bin, which you can't see very clearly there. But they were obvious. So if you plot only the very fastest bit of the distribution, up to 300 microseconds, as opposed to up to 1.5 seconds, you see a distribution like this. And that is, of course, there's a big excess in this bin for things above 300 microseconds because there are many longer shuttings as well. And you see that there are many short shuttings. After a little while, we notice that if you plot it on yet a different scale, up to 5 milliseconds, you can see that there's an excess of intermediate shut times, which we'd missed at first, things around a millisecond long, like this shutting here, not the very short type, but it's a much smaller component, and that's why we missed it. Incidentally, once we'd noticed that that was there, we went back and refitted everything with 3 exponentials rather than 2, simply because we knew that in principle there are 3 exponentials there, 3 detectable exponentials at least. And it doesn't matter if any individual case you get a significant, statistically significant, terrible expression, reduction in the, or increase in the goodness of fit by fitting 3 rather than 2. It's irrelevant. If then we know there are 3, we should fit 3, whether or not it produces a big increase in the goodness of fit. But a virtue of doing the fitting the way we do is that you don't have to decide how many exponentials to fit to distribution, because you don't fit them to distributions. Now, as soon as the log plot came along, again, an innovation by Carl Magleby, I think, the distribution of the same data, plotting the distributions of the log times, look like this. You can see the fast component very clearly. You can see the slow component very clearly. You can also see the intermediate component very clearly, all on one plot. If we'd plotted it that way initially, we'd never have missed that intermediate component. So this is our distribution. We can fit it with 2 exponentials, which is what we did at first. That's the dashed line. Or we can fit it with 3 exponentials, which is what we did subsequently. And you see that it fits a great deal better. Not only a great deal better here where the intermediate component is, but better to the fast shut times as well. You see the faster shut times falls from 57 microseconds down to 46 microseconds when fitted this way. We can also fit things like the distribution of the length of bursts of openings, these whole bursts, including the shortest shuttings, which there are quite a lot here. In a wild type receptor, it looks something like this. You can see there's at least 3 components, probably 4 or more. And you can see that if you fit this particular mutant, which is a mutant that causes slow channel congenital myasthenic syndrome in man, you can see that the bursts are considerably longer, or many of them are much longer. You can also fit the distribution of the apparent number of openings per burst. Of course, this is going to be greatly influenced by missed short shuttings, but it's a thing that one does sometimes. In the early days, we plotted them like this. This is the number of apparent openings in a burst. And the dashed line there is a fit of a single geometric distribution. You can see it doesn't fit very well. But if you fit a mixture of 2 geometric distributions, the dashed lines are fitted barely visible, it fits very well. And this was a common finding, still is, that there's a component of bursts that has only 1 opening in each of them, roughly speaking. In the case of glycine and nicotinic receptors, these are probably the monoliganded openings, predominantly at least. So The first look at the data would be to look at empirical fits. Here's an example from a glycine receptor with done at a single concentration, 10 micromolar. We can just display the distribution of durations there and fit exponentials to it in a entirely empirical way. The resolution there was 30 microseconds, so this has been imposed on the data, so there's nothing less than 30 microseconds there. That gives a good fit with 2 or 3 exponentials, and you can get their time constants and areas, but these time constants are not easily interpretable in terms of the exact mechanism. So what we do now is a better way. We don't fit one concentration, we fit several concentrations simultaneously. These are separate patches with 10 micromolar glycine, 100, 300, and 1,000. We'll see why that gives you a big advantage in a short while. We postulate a mechanism which we're going to test eventually. We're not saying it's right, we're just testing it. This was 5 binding sites, each of which could open. We use the maximum likelihood fit in HJCfit to calculate the rate constants, the elements of the Q matrix, which fit the data best. And we find something like the opening rate for the fully liganded receptor is 7,000, 130,000. The shutting rate is 1,200 in that case. Because we go straight from the list of open and shut times to the estimates of the rate constants. We don't have to dissipate any distribution at all. Of course, it's advisable to do so to check on that they look good, but we don't have to. So what we've got to do now, having got these rate constants, is to check whether they fit the observed data accurately. The maximum likelihood fit is based largely on this paper, the ones we had in Phil Trans A, Physical Sciences, 1996, because this gives all the things you need to do the fitting with the exact missed event correction. The calculation uses joint distributions of open and shut times. Notice that the HJCfit doesn't use burst lengths at all. It just uses the list of open and shut times. Notice also that when it's done this way, essential information that arises from the fact that the length of an opening is negatively correlated with that of the adjacent shut times is taken into account correctly. So that means that all of the information in the record is used. These are the correlations that we talked about in an earlier talk. They're part of the mechanism and they contain useful information. So here's the first 2 openings in a record and the first shutting. A very short bit of a very long record with any luck. So what do you mean by the likelihood of that sequence? Well, the probability, we start with the probability that the first opening was 2 milliseconds, of course. they won't be exactly 2 milliseconds. What we use is the probability density, that it's equal to 2 milliseconds. And we multiply that by the probability that the first shutting is 10 milliseconds and the first opening was 2 milliseconds, because the length of that first opening will influence this probability as well as the length of the shut time. And we multiply that by the probability that the second opening is 5 milliseconds and the first two events were as they were. These probabilities, of course, depend on the values of the rate constants, the elements of the Q matrix, and they depend on the resolution of the observations. So they're calculated by the methods of Hawkes, Jalali, and Cahoon, 1990 and 92. That's what HJC stands for. And because we've got the rate constants, we can make sensible physical deductions from them. Whether or not the mutation affects the binding site, we need the values for the underlying rate constants for the binding reaction, separated from those from the gating reaction. So this avoids entirely the difficult step between fitting exponentials to a distribution and inferring the value of what we want to know, the underlying rate constants. The equation for the likelihood was, it can be evaluated from the known resolution in the Q matrix. This is what the Schrodinsky paper showed how to do. And we start with an initial vector of size 1 by Ka, the number of open states, because we're beginning with the first opening, and we need the probability that the first apparent opening starts in each of the individual open states. We multiply that by the GAF of the first open time. This gives the probabilities corrected properly for the fact that we're missing short openings. That's what the E bit there specifies. The probability that we stay within the open states, subset of open states, that's the A set, for a time T01 and eventually leave for a shut state. That's what that elements of that matrix gives. That, of course, is a 1 by Kf. That is a Ka by Kf matrix. So the product of those is a 1 by Kf matrix, and this forms the initial vector for the first shut time. GFA of T shut 1 gives you the probability densities for staying within the shut states, or appearing to stay within the shut states, for a time TS1 and eventually leaving for an open state. That whole thing is a 1 by Ka vector, which gives you the appropriate entry probabilities for the second opening, GAF of T02, and so on. And you do this monster multiplication up to your last opening. The channel then ends in the shut state, so you sum over shut states, and you get a scalar quantity, which is the likelihood of that sequence. There's an awful lot of computation involved in that, of course. So we can summarize what you need to do in an HJCfit analysis. Define the mechanism to be fitted. Specify the data sets to be fitted. You can also, in the Windows version of the program, you can also specify that you want to simulate data rather than fitting real data. Simulations can be very useful for testing things, as we'll see. You specify the resolution to be imposed. That resolution has to be imposed on the data by going through it and removing any short shut times that are below that resolution and concatenating them with the open time on each side of that short shutting to produce a record with a consistent time resolution. You inspect the stability plots. And now we come to a tricky bit now, because ideally the entire record would be from one single ion channel. But it's rare that you can guarantee that. Well, you can at high concentrations, but at low concentrations, you generally can't guarantee that all of the openings that you see come from the same ion channel. And that means you have to specify a thing, a T crit, a critical time, which is such that any open time longer than T crit is, well, any open time, any shut time shorter than T crit is deemed to separate channels, openings that come from the same ion channel. Any time longer than that, you can't guarantee that the next opening is the same channel as the previous one. You have to decide whether to set a long open times as unusable. That only occurs if you forget to shut a channel when doing the analysis, but it's quite useful to compensate for errors that you might make while doing the scanning. You've got to specify the ligand concentration for each data set, of course. You've got to specify which rate constants are to be constrained to be a fixed multiple of another one. You can constrain two rate constants to be equal if you want to constrain the equilibrium constants to be equal, for example. You can also, in HJCfit, fix one of the rate constants to produce a specified EC50. You've got to specify initial guesses for each of the rate constants, except ones that you choose to fix. If you choose to fix any of them, that's not generally advisable, but it has to be done sometimes. And then you set it going and wait for it to converge. It can take hours or it can take a minute. And then when you get to the end, you get a list of fitted rate constants, and the essential bit is then to check whether or not they describe your data accurately. And you also want to calculate the likelihood standard deviation and correlations between fitted rate constants. So to reiterate the step about fitting low concentration records, long shut times can't be included in the analysis, because if the channel reopens after a long shut time, you can't be sure that it's the same channel as that's reopened, or whether it's a different channel that's opened. So the likelihood is calculated separately for groups of openings that all arise from the same channel. So, and that's defined by the critical shut time, which you specify before you start the analysis. Of course, this removes information about the frequency of openings in low concentration records. You can't say what it is. But there are several things you can do about that loss of information. You can fix one of the rate constants, a binding rate constant. That's clearly not a last resort to fix a rate constant because you don't really know its value. You can obtain a rate constant by using its value, using a value which produces a specified macroscopic EC50. EC50s from macroscopic measurements are not generally very reliable. So that's not ideal, but it's better than nothing if you have to do it. Another method you can use to recover some of that information is to use CHS vectors. I'll describe what they are in a minute. But the best method is to fit high and low concentration records simultaneously, because the Q matrix ought to be the same regardless of concentration, except of course for the association rate constants. But all the other elements of the Q matrix should be independent of concentration if the rate constants are indeed constant. And that means you can get much more information by fitting several records simultaneously recorded at different concentrations. This was our expression for the likelihood we're trying to maximize. At a low concentration, the long shut time that follows the end of a burst of openings will appear to be shorter than it should do if the next activation arises from a different channel. But what we can say is the true length of that long shut time must be at least as big as the observed gap. Must be at least T crit if we've specified T crit. And that means we can incorporate that knowledge into the likelihood by using an end of burst vector, replacing this unit vector by this thing which integrates the shut times from T crit up to infinity. And that's a CHS vector. And you can do something similar for the beginning of the group of openings that you're calculating the likelihood for. This is from the Shredinsky paper, so that's where CHS comes from. And that makes a useful improvement. So we start with an initial guess and we maximize the likelihood. This shows the actual time, the actual course of that maximization in one particular case. Of course, it only shows it for two different parameters, the shutting rate alpha 2 and the opening rate beta 2 for the case of a nicotinic receptor. If we're fitting 9 free parameters, of course, this ought to be 10-dimensional, but we're just looking at the course for 2 of them because the opening and shutting rates are particularly interesting. We started with an initial guess here. The likelihood went up very rapidly initially by trying different values. It ended up here with very fast values for alpha and beta 2, but then it crept along just slowly increasing until you end up with the maximum there, which corresponds to smaller values for the opening and shutting rate constants. So along that ridge, the values of the opening and shutting rate constants change roughly in parallel, so that their ratio does not change much, and the likelihood increases only slowly. This is a sign that alpha and beta are correlated. This is the setup we've seen before for specifying everything you need to do the fit. We'll come back to that method, that question of correlation between estimates in a minute. This is a mechanism for a nicotinic acetylcholine receptor, which includes monoliganded openings. It includes, in fact, two different sorts of monoliganded openings because it doesn't assume that the two subunits of the receptor are the same. So we have two different monoliganded shut states, two different monoliganded open states. And you have, of course, diliganded openings. The opening rate constant is about 50,000 in this case. And this is a good deal faster than our very earliest estimates, but they were crude. Around 50,000 is what we think it is now. So this was for the wild type receptor. These are the rate constants for this slow channel myasthenic syndrome mutant, which produces longer bursts of openings, as we've seen. We can summarize the results by saying that the total dissociation rate is 14,000. That's the sum of those two dissociation rates for the wild type, but it was only 4,600 for this mutant. The difference in the opening and shutting rates was smaller, so the main effect of the mutation is to slow agonist dissociation from the shut state. And we've achieved our objective of separating affinity and efficacy. So what the output of that looks like is something like this. There are 14 rate constants in that mechanism, but only 9 free ones. And since only one concentration was fitted, we were forced to fix one of the association rate constants at a 10 to the 8 per molar per second, which is a typical value for acetylcholine, but of course we don't know it. 3 of the rate constants were constrained so that the first and second binding steps are the same, and one of them is determined by microscopic reversibility, so there are 9 free parameters. This lists all 14 parameters. The initial guess for them, the final estimate for them, the approximate standard deviation for them. We'll come to how you get that in a minute. So the opening rate constant was 50,800, standard deviation of 1840, and that's not easy to interpret. It's better expressed as a percentage. So it's 50,000 plus or minus 3.6%. For the shutting rate, plus or minus 4.1%. So one of these dissociation rates is rather well defined. Most of the rest are not so well defined. This opening rate constant for one of the monoliganded ones has a coefficient of variation of 25%, so that's not very good at all. We can also get the correlation coefficients from the Hessian matrix. In a way that I described before. we see from this that there's a strong correlation between the value of the shutting rate for the diliganded receptor and for the opening rate. There are correlations for some of the other ones as well, but this is the strongest correlation as a rule. That was why the final estimates crept along that ridge in the likelihood surface. It makes sense that there should be a positive correlation between them because the burst length is well defined, but the individual openings and shuttings are not so well defined because you are missing short shuttings during the burst. So there's some ambiguity as to whether the burst length is made up of a lot of short openings or a few longer ones. If beta 2 is large, the opening rate is large, there will be more reopenings of the channel, more openings per burst. So to keep the burst length the same, alpha 2 has to be fast as well, because that means that the individual openings would be short. Conversely, if beta 2 is smaller, the opening rate is smaller, there won't be so many openings per burst, but alpha 2 will also have to be smaller because that will mean that each individual opening is longer. So this negative correlation makes perfect sense. And notice, though, that despite the fact that they're highly correlated, these are among the most precisely determined of the parameters. So how do we get that correlation matrix, you may well ask? Well, it's a very standard method. And it depends on the curvature of the likelihood surface near the maximum. If the curvature is higher in that likelihood surface, then it falls off steeply. The likelihood falls off steeply for a small change in the parameter values. That means that parameter is well defined. If the likelihood surface is very flat, then that means you can change the parameter estimates a lot without changing the likelihood very much. And so the parameter is not well defined. The curvature of a surface is measured by the second derivative. That can be defined for any number of parameters in this way. And that derivative this is a matrix, of course, because it refers to the ith and the jth free parameter. And this is estimated, this is the likelihood at the peak of this is the curvature of the likelihood surface at the peak, at its peak. And if that matrix is inverted, that's called the information matrix, then you can get the covariance matrix, and the diagonal elements of this matrix are the variances of the parameter estimates. You take their square root to get the standard deviation. The off-diagonal elements are the covariances, and they can be converted very simply into correlation coefficients, which is the way they're normally looked at. If we look at the likelihood surface for the opening and shutting rates alone, in order to make this plot, we fixed the values of all the other parameters at their maximum likelihood values and just looked at the surface for the opening and shutting rate alone. And it looks like that. The peak is actually here. progress of the fit we showed earlier went up rapidly, came to these very fast values, and then progressed slowly along this ridge to the peak. For the purposes of looking at errors, it's probably best not to look at it in this three-dimensional way, which looks very nice, but is not easy to read things off. We can plot that as a contour map. The peak of the hill is here. That's an opening rate of 50,000, a shutting rate of 1,500. And these are the contours. In fact, it's possible to estimate the errors not so much from, not as the variance of these things, which is what you get from the covariance matrix, but you can calculate things called likelihood intervals. The likelihood interval for the shutting rate constant alpha would be the value which was tangent to that contour there. The likelihood interval for the opening rate constant beta would be the value that is tangent to that contour here. Or if you want greater certainty, you could use these bigger contours. The advantage of likelihood intervals, of course, is they don't have to be symmetrical. You can see that the upper limit is going to be a bit bigger than the lower limit. But that's, in general, not really necessary. Our general purpose curve fitting program will always give you likelihood intervals, but they will be very slow to calculate in this case, so HJCfit doesn't. The contour for which is less than the log likelihood, these are log likelihoods now, not the likelihoods themselves, because if you actually calculate the log likelihood, the number would be immense otherwise. This contour for which is 2 log likelihood units below the maximum actually corresponds in a rough sort of way to a 95% confidence interval. So next time we go on to fitting some real data with some real mechanisms.